We have seen classical circuits. They were made up of bits, that means classical bits, and they had wires running through them, which represented storage space. Now it's the time to introduce quantum circuits, and you might notice the differences. Wires will carry qubits now instead of bits. Gates will be unitary operators because we are only allowed to apply unitary operators in a quantum circuit. And we have discussed some of these unitary operators. We know how they can look, numbered, and so on. We will see many later. Third, the computation can end with a measurement. It depends. If you want a quantum output, then you don't need to measure. But if most of the cases, we would need a classical output. And in the case when you need a classical output, you will measure the qubits, some of them or all of them, and that will be your answer from the quantum circuit. These are the main differences between a classical and a quantum circuit. Let's see an example for a quantum circuit. A sample circuit will start with some inputs, and then I will have a few ancilla qubits. Let's say this is my work registers and I start with cat 0. I can apply a header mode on my input, then probably a C0 on my ancilla qubit, then I can apply probably a C0 with control qubit as the ancilla qubit. Then I can have a complicated unitary which I can apply on all the qubits. So this you might think of as a subroutine whose specification might be given differently. It's a big unitary. We will be interested in how fast we can apply this unitary, what kind of gates are there, but this can be given separately. This is how a general circuit will look like. It will finish by a measurement. Let's say in this case, we only measure the first two qubits, and this will be our classical answer. This is a simple quantum circuit. These are the various elements you will see when you look at a quantum circuit. Notice this symbol. This is saying that we have measured these qubits. This is a C0 gate. This is a C0 gate. Here, this dot represents the control. If I look at this C0, first qubit is the control qubit and third qubit is the target qubit. Second qubit does not take part in this. In general, when we specify the action of a circuit or a gate, it is easier to specify its action on a basis. Remember, gates or circuits are linear operators. I'm talking about circuits without measurement. That is the last part. Let's not worry about that. These things are linear operated. These are just collection of unitaries. So it is enough to specify action on just a basis. In particular, most of the time we will choose the standard basis. That means we will only mention what happens on the classical space. That is good enough to specify the complete action. For example, If you take poly X matrix, remember its representation was 0, 1, 1, 0. I would just say that it takes state 0 to 1 and 1 to 0. That is good enough to tell me the entire poly X matrix. If in general, if this is the state given as an input to X operator and apply X, the answer would be alpha 1 plus beta 0 by linearity. This is a simple example. You can convince yourself what happens in the case of C0 gate. This is what we are going to follow in most of the discussions. Sometimes we will choose one of the bases to be classical. Sometimes we will choose all bits to be classical and specify their action. But assuming this principle, you should be able to figure out the complete action of the circuit. Let us take a non-trivial example of a quantum circuit, which does some useful operation. We will try to make a circuit which adds two binary strings. This is definitely useful. Let's see a quantum circuit which can add two binary strings. First, remember, how would you add classically two binary strings? Let's say classically two binary strings are 0, 1, 0, 0 and okay, let's take a slightly smaller one, 1, 0, 1, 0, 0 and other is 1, 0, 1, 1, 0. If I want to add these, I will add them place-wise. This is the standard addition which you might have learned in class 2 or 3. 0 with 0, you get 0. Now remember that these are Boolean strings, so I will add accordingly. These are represented in base 2. 0 plus 1 is 1. When you add 1 plus 1, this will give you 0 and I will have a carry here. Again 1 plus 0 plus 0, 1. Now again 1 plus 1 is 0 with 1 carry. This gives the final answer. Make sure that this addition on base 2 is clear. If you looked at this, then essentially there is just one subroutine which gets applied again and again. And that subroutine is about adding two bits at a place. When we add two bits at a place, the output would be one answer bit and one carry. This is called a half adder. Again, let me describe the action of half adder. If I am adding 0, 0, then my carry would be 0, answer bit would be 0. If I am adding 1, 0, then my carry would be 0, answer would be 1. If my input is 0, 1, then my carry would be 0, answer would be 1. And the only case when the carry bit will be set, when I input 1, 1, then carry would be 1 and answer would be 0. This is a half adder. This adds things coordinate wise. Then you might ask how to convert it into complete addition. And you might have guessed, I leave it as an exercise. You should try it. It's a classical thing. If you can't, then you can look at the circuit in the notes. This tells me that my problem has now reduced. If I want to add two binary strings, two Boolean strings, then my job is to add coordinate wise. That means I need a circuit for half adder. If I can build a circuit for half adder, then I can complete the action. Remember, on 0, 0, I get 0, 0. On 1, 0, I get 0, 1. On 0, 1, again I get 0, 1. On 1, 1, I get 1, 0. This is carry. This is answer. From now on, we will assume that most significant bit is carry. And for the sake of simplicity, we will have a 4-qubit circuit. Let's say A0 and A1 are the inputs. It will have 2 ancilla qubits and answer would be computed here. That is what we are targeting. This is our aim. How to do it? We don't care about this and this qubit. I need to find the circuit so that my answer is computed here and carry is computed here. This will be a half adder. Again, there are two things to compute, answer and carry. Let's take them one by one. First thing is the answer. Take some time and tell me if you recognize a classical operation which is happening here. Remember, we will only give you a classical description and you can always use linearity to find the action of the complete circuit on any state. Let's only worry about classical states now. We know what half adder should do on classical states. And the question is, what is its action in terms of computing the answer? Notice for 0, 0, it gave me 0. On 0, 1, it gave me 1. On 1, 0, it gave me 1. And on 1, 1, it gave me 0. If you notice carefully, this is a gate which you have seen. This is called XOR or exclusive OR. That means answer bit is 1 if and only if exactly one bit is 1. Fortunately, we have seen the quantum equivalent of XOR. Do you remember what was the quantum equivalent of XOR? This was called a C0 gate. Simply, we want to take C0 of the two input qubits which I called A0 and A1. The difference is that if I take C0 of A0 and A1, then I will compute it on one of the wires of A0 and A1. But I wanted to keep them the same. I want to compute them on a different qubit, and the way to do it would be to notice that A0 plus A1 can be written as 0 plus A0 plus A1. That means I will take a third qubit and C0 twice. I will use two C0 gates to perform this A0 plus A1. That means my circuit will look like A0, A1, 0, 0. And use A0 to first flip the third ancilla qubit, then once again do it. This means this will be A0 XOR A1. Notice that this is only the action on classical states. For action on quantum states, you have to use linearity. This works for the answer qubit. What about the next carry bit. Let's see once again the action. On 0 0 carry bit is 0, on 0 1 0 1 0 again 0, only it is 1 when the input is 1, and you can again recognize this is the AND gate classically. It's a simple AND gate, but how can we do it quantumly? Pause the video and think if you can execute AND gate using CC0. Some thought will show you that AND can be obtained of 2 bits just by taking C0 with 0. This will give me A0 and A1. This bit will be 1 if and only if both controls are 1. This is the definition of CC0 gate. Now we have got our full circuit. Let me draw it. First, my answer qubit will come. This is this circuit, and then I will do a CC0 gate. You see that it is controlled by 2. I have marked it with both the qubits, and then this will give me carry, this will give me answer. We know now the action of half adder on any classical states or basis states. What happens if there are non-classical states? If I start with some state, let's say, so clearly the last 2 qubits are fixed, the first 2 qubits are the only things which can be changed. Let's say if the first 2 qubits were in this state, notice that any state of first 2 qubits can be written like this, then by linearity the answer would be in the case of half adder, again I will get 0 1, but on 1 1 I will get 1 0. This will be the action because I have just extended action by linearity. Final output of my half adder. I have given you an example of quantum circuit. There are questions about how or what quantum gates are allowed and we can apply. We will take this question in the next video. Thank you.